Hi, I'm Cassie, and today I'm going to walk you through everything you need to know about aldehydes and ketones for the MCAT. Now, the number one topic that students I tutor say that they struggle with is organic chemistry. Studying organic chemistry for the MCAT can feel really overwhelming. You might think that you need to know everything you needed to know for your college orgo classes, and that's just not the case. The best way to study orgo for the MCAT is to actually go through all the topics listed on the AAMC official outline for the MCAT test. Now, if you haven't seen that outline before, I'll put the link in the bio of this video. But also, you can just search AAMC official outline and you'll find a document that looks like this. What's on the MCAT exam? Now, this is an over 100-page document that goes through each section of the test and lists every possible topic that they could test you on for that section. So on the right here, I've pulled out part of the outline. This is from the Chem and Phys section. And section 5D is about structure, function, and reactivity of biologically relevant molecules. Now, under this section is where we get into the heart of a lot of the orgo content for the exam. One of the absolute biggest orgo topics that shows up on the exam is aldehydes and ketones. So notice here that the AAMC has literally listed everything that you need to know about aldehydes and ketones for the exam. So starting with, a description of what aldehydes and ketones are, how we name them, what their physical properties are, what kinds of reactions aldehydes and ketones can take part in, what are just some general principles about aldehydes and ketones that we need to know. So if you walk through all these topics with me now, you should feel confident going into the MCAT that you know absolutely everything about aldehydes and ketones you need to know for the exam. Okay, so let's go ahead and get started with our first section here, which is going to be our nomenclature of aldehydes and ketones, or naming, and their physical properties. When we talk about naming aldehydes and ketones, we're talking about the IUPAC, which is just an abbreviation for this international organization that decided how we're going to name organic chemistry compounds. Now, in order to be able to name an aldehyde and a ketone, first we need to understand their general structure. Aldehydes and ketones are going to be similar in structure in that they both have a carbonyl group. So if we have our aldehyde over here on the left, it's going to have a carbonyl group, which is just a carbon double bonded to an oxygen. And our ketone is also going to have that same carbonyl group. The difference is going to be what's attached to that carbonyl carbon. In an aldehyde, we're going to have one R group. Remember, an R group just means some other compound, and one hydrogen. Versus in our ketone, we're going to be attached to two different R groups. So that means two different carbon-based compounds. So the only difference is the aldehyde has to have at least one hydrogen. So in terms of how we name these molecules, it's actually pretty simple. Let's first just focus on if we have an aldehyde or a ketone on their own, not as a part of a bigger molecule. So in that case, the name for our aldehyde or ketone has two parts, a prefix and a suffix. So starting with our prefix here is just going to represent the longest carbon chain that includes the carbonyl group. So here you need to have memorized how to name your alkanes, right? Your hydrocarbon chains. And so if we have one carbon chain, we know that that's called methane. If we have a two carbon chain, we know that that's called ethane. 3 is propane, and so on and so forth, all the way up to 10 carbons. And the same thing is going to apply for ketones. Now, for our suffix, they're going to be different for aldehydes and ketones. So our suffix for aldehydes is going to be al, and that's easy to remember because al are the first two letters of aldehyde. And then our suffix for ketones is going to be one, or one, which is also easy to remember because that's the ending of ketone. Let's take a look at how we name some simple aldehydes and ketones. Let's say I have an aldehyde that looks like this, the simplest possible aldehyde, which would just be our carbonyl group. It's going to be attached to two hydrogens. Now, what's our longest carbon chain here, including the carbonyl? Well, we only have one carbon, it's the carbonyl carbon. So our prefix here is going to be methane. Okay, so we're going to take methane. And then our suffix, since it's an aldehyde, is going to be al. Now, the only thing we have to adjust is you're just going to drop the E. So you're going to cross out off the E. And so this aldehyde is called methanol. Now, methanol is the IUPAC naming for this compound, but a lot of compounds in orgo, we also give them common names that we use on a day-to-day basis rather than these fancy scientific names. And you might have heard methanol by its common name before, which is formaldehyde. Now, let's try naming a slightly more complex aldehyde. So first thing, what's our prefix? So let's count our carbons and find the longest carbon chain that includes our carbonyl. Well, we're always going to start at our carbonyl here. 1, 2, 3, 4. So our longest carbon chain is 5. So we know that we call hydrocarbon chains with 5 carbons pentanes. And then, of course, we cross off the E and we add our aldehyde ending, our aldehyde suffix. So this aldehyde is going to be called pentanol. Now let's do some examples of naming ketones. So let's say I have the simplest possible ketone here. So we've got our carbonyl group. And then for our two R groups here, we're just going to have methyl groups. Remember, a methyl group is CH3. Again, why would that have meth as the prefix for that? Well, because a methyl group only has one carbon, right? There's one carbon and 3 hydrogens. So how would we name this ketone? Well, let's count our longest carbon chain. That includes the carbonyl carbon. So let's count our carbons here. We've got, let's see, 1, 2, 3 carbons. Now to name a hydrocarbon chain with 3 carbons, we would call that propane. Okay, so let's go ahead and write that. Propane would be our suffix here. What are you going to do to the E? You're going to chop it off. And then you're going to add our specific ketone suffix, which is going to be ONE or ON. This ketone is going to be called propanone. Now, you might recognize this ketone by a different name, its common name, which is acetone. And acetone comes up really commonly in the MCAT, so you definitely want to recognize it by either its common name or by its IUPAC name. Now, one way that ketones are a little different than aldehydes is that they can appear in the middle of a molecule. So let's draw a molecule where that's the case. So here in this molecule, if we go ahead and number our carbons, we always want a number on the side that's closest to our ketone, right? Because we want the carbon that's part of our ketone to have the lowest possible number. So if we number it from the left, we'd get 1, 2, 3. Our ketone would be at number 4. But if we number from the right, we get 1, 2, 3. Our ketone is located at carbon number 3. So that's what we're going to want to go with because it has the lowest possible number. And then, of course, we want to count how many carbons we have total. So we keep going. We get 6 total carbons here. 6 corresponds to hexane, but we're going to drop that E and we're going to add that own ending. But then we're also going to specify where our ketone is. Otherwise, how would we know, right? So we're going to specify that this ketone is located at position 3. So this ketone is called 3-hexanone. Now, comparatively, if we look back at our aldehyde over here, notice it's always going to be on the end of the molecule. So it's always going to be off of carbon 1. So we could write it like this, 1-pentanol, but that's sort of redundant. So to save space, since a lot of times we get some complicated molecules, we don't even write the 1. We just write pentanol. So important takeaway here for naming molecules for the MCAT. Once you've identified your highest priority group, you need to make sure that you number the carbon that highest priority group is located on, unless it's something like an aldehyde that always falls at carbon 1 at the end of a molecule. Now, that's naming an aldehyde or a ketone when you just have an aldehyde or a ketone. What happens when you have an aldehyde or ketone as a substituent group of a larger molecule? How would we name them in that case? Now, let's say we have a molecule that has an aldehyde and a ketone. So first, let's identify where our aldehyde and our ketone is. So our aldehyde is going to be here on the right side of the molecule, and our ketone is going to be over here on the left side of the molecule. Well, we know if it's an aldehyde, then its suffix of the molecule would end with al, but if it's a ketone, it would end with -one. So how do we decide? Do we use the aldehyde or the ketone suffix for the molecule? Well, that depends on which group is more reactive. So the IUPAC, they make a priority list for which functional group takes priority for the suffix in a molecule based off of how reactive each functional group is. So here we can see that priority list. If we take a look and look for aldehydes and ketones, notice that they're about in the middle of this priority list, with aldehydes having slightly higher priority than ketones. Now, why is that? Again, this list priority is based off of reactivity. Aldehydes, because they always have a hydrogen as one of their side groups, are going to be slightly more reactive than ketones. If you imagine it's easier for another molecule, like a nucleophile, to come in and attack that aldehyde at the carbonyl group, versus in a ketone, that carbonyl group is sort of protected by the two R groups, and so it's harder to attack. So we know in this case, where we have our aldehyde and our ketone, that our suffix is going to get the name of the aldehyde since it has a higher priority. Now remember, when we're naming, we follow the same basic formula. We just decided that our suffix is going to be based off of our aldehyde. So we know that our suffix here for this molecule is going to be Al. Now, our root is going to be our longest continuous carbon chain that contains that main priority functional group. So in this case, let's take a look. We've got 1, 2, 3, 4, 5. So our longest continuous carbon chain is going to be 5 carbons. We know that our root name for something that has 5 carbons is going to be pentane. And just like before, we're going to drop that E. And then substituents are going to be any other functional groups we have, the ones that weren't our highest priority group. So in this case, we only have 2 functional groups, our aldehyde, which we've already used to name our suffix, and our ketone. So when a ketone is not our highest priority group and we're using it as a substituent, we're going to use the prefix either oxo or keto. Either one is totally correct. So in this case, I'm just going to write oxo here. And then we want to know where that functional group is in the molecule. So in this case, we see that ketone is right here at carbon number 4. So we're going to call this 4-oxopentanol. Okay, so now that was an example of when an aldehyde is our highest priority functional group. Now let's take a look at an example where our aldehyde is not our highest priority functional group, where it's just a substituent. So here we're looking at a molecule. We notice that it has 2 main functional groups. So on the right side of our molecule here, we have a carboxylic acid. And of course, you can recognize that by the carbonyl group, the C double bonded to the O, with the hydroxyl group attached on one side, and it bonded to something else, some other R group on the other side. And then, of course, on the left side of our molecule, we see that we have an aldehyde. Now let's take a look back at that chart that shows us the priority for our different functional groups in terms of naming. Okay, so here we see the naming chart again. Notice that our carboxylic acid is the highest priority functional group that we have. It's all the way at the top here. And when a carboxylic acid is the highest priority functional group, we of course are going to use it as a suffix. So our suffix here is going to be oic acid, since that's the highest priority group. And then our root, let's go ahead and count our longest continuous carbon chain with that carbonyl carbon of our highest priority group. So here we go. We're going to start there. 1, 2, 3. Okay, so our longest chain is 3 carbons. That means we have propane as our root. Of course, we're going to drop that E, so it's just going to be propan. And then for our substituent, of course, we have our aldehyde, but we have to figure out which carbon our aldehyde is off of, so we can show that where it is on the molecule. Well, if we take a look here, we notice that our aldehyde is located at carbon 3. So we're going to have 3. When an aldehyde is a substituent, we're going to use its prefix. Now, there are 2 interchangeable prefixes you can use for an aldehyde. You can either use oxo or you can use formyl. So I'm going to use oxo. So I'm going to call this 3-oxo-propanoic acid, but I could have also called it 3-formyl propanoic acid. Okay, so that covers our basics for naming aldehydes and ketones. Okay, so what happens if we have more than one substituent? How do we name the molecule then? What order do we put the substituents in? Well, let's say that we take our molecule here and we add a methyl group onto carbon 2. So how is that going to change the name of our molecule? So you're always going to put your substituent groups in order of the number of carbon they're on. So since this methyl group that we added is on carbon 2, that's going to come before carbon 3. In the name of the molecule, it's going to go before the aldehyde, before the 3-oxo. So we end up with 2-methyl 3-oxo-propanoic acid. Now, you might ask, what happens if we have 2 groups off of the same carbon? How do we order them then? Well, then we're going to go by alphabetical order of the names of the group. So we already have a methyl off of carbon 2. Let's say we add an ethyl as well. So there's our ethyl off of carbon 2. Now, since the E from ethyl comes before the M from methyl in the alphabet, we're going to put the ethyl before the methyl in our name here. So let me take a second to zoom in on the fact that just like molecules where aldehydes are the main functional group, when carboxylic acids are the main functional group, as is the case in this molecule, they're always going to be at the end of the molecule, right? Just by the nature of the fact that you have that OH hydroxyl group on a carboxylic acid, that group is always going to be on the end of the molecule, which means you never have to specify the carbon number that the carboxylic acid is off. So notice we just say oic acid. We don't say like 2-oic acid or 3-oic acid. It's always going to be at carbon 1, just like aldehydes are always going to be at carbon 1. So we just leave off that 1 and write oic acid. So far we've covered how you name aldehydes and ketones that only have single bonds. But what happens if you have molecules with aldehydes and ketones that have double bonds? In other words, if you have alkenes, how does naming change when you introduce those double bonds? Well, first thing you need to know is when we have alkanes, like this molecule pictured right now, we name the root with an AN, as in propane, right? Propan, propanoic acid in this case. So here you say we've got the AN. So when we have an alkane, we use AN in the root. But when we have an alkene, what do you think we're going to use? Well, we're just going to change that A in the alkane to an E. So if this molecule had a double bond in it, it would be propan with an EN, propanoic acid. So now let's take a look at an actual molecule that has, let's say, a ketone and a double bond in it. So first, let's go ahead and identify our highest priority group here. We have 2 functional groups. We have first our ketone on the left here, but then we also have an alkene on the right side. So which one takes higher priority? Well, if we look back at our table here, we find ketone in the middle, just like before, and then alkene is farther towards the bottom here. So ketone is going to be our highest priority functional group. So let's go ahead and write that in for our suffix for the molecule. And then, of course, we have to label where is our ketone, right? Because it could be a huge molecule and the ketone could be somewhere in the middle. So let's go ahead and count our carbons, figure out also our root at the same time. Well, we always want to start counting our carbons on the side closest to our ketone. So this is going to be carbon 1, carbon 2. So our ketone is located at carbon 2. We're going to go ahead and specify that this is a 2-one. And then let's continue counting our carbons. We've got 3, 4, 5 carbons total. So if this were an alkane, that would be like pentane. But this isn't an alkane, right? We have a double bond, which means we have an alkene. So instead of doing pentane and dropping the E, we're going to do pentene and drop the E. So this is going to end up as pentane. And then we need to specify, just like we specified where our ketone was, we need to specify where our double bond is, right? Because it could be anywhere in the molecule. So if you notice, our double bond is located here between carbons 3 and 4. So we don't need to specify both of the carbons. We always just specify the first carbon that the double bond is located at, the lowest number carbon. So in that case, that's going to be carbon 3. So we have 3 pentan 2-one at this point, but we're still missing something. We're going to have to specify whether we have an E or a Z isomer around our double bond. So how do we determine if an alkene is an E isomer or a Z isomer? Well, it's actually pretty simple. What we're going to do is we're going to take a look at the substituents or the groups attached to the 2 carbons in our double bond. So let's take a look at this molecule. Here, our first carbon, carbon number 3 in our bond, is attached to another carbon. And of course, it's also attached to a hydrogen. It's just not shown here. Now, our second carbon in the bond, carbon 4, we see that it is just like carbon 3 attached to another carbon with the methyl group here, and it's also attached to an invisible hydrogen. Okay, so now that we've identified what substituents are attached to the 2 carbons in the double bond, we're going to compare the priority of those substituents and whether the highest priority groups are on the same side or the opposite side. So how do we determine the priority of these groups? Well, we use something called the Cahn-Ingold Prelog rules, but all you need to know about the Cahn-Ingold rules is that they base priority off of atomic number. So the higher the atomic number, the higher the priority. So in this case, what has a bigger atomic number, carbon or hydrogen? Well, if we take a quick look at the periodic table, remember this is the periodic table that they actually will give you on the day of the MCAT. So it's really important that you get comfortable using this periodic table. So hydrogen, we see its atomic number is 1, that number above it, right? Which is also the number of protons the element has. And if we compare that to carbon, its atomic number is 6. So carbon is going to be our higher priority substituent group attached to the carbon in our double bond here. Now we have to decide our highest priority groups on the same side or the opposite side of our double bond. Well, here we see that our highest priority groups are carbons. They're both on the same side of the double bond. Now, when that happens, we have a Z isomer, and I like to remember that as they're on Z same side. So this molecule is going to be a Z isomer. So we're going to write that Z out front. Now, what would the E isomer of this molecule look like? So everything's going to stay the same in terms of here we have our ketone, still going to be at carbon 2. And here we've got our double bond. The only difference that we would need to change is we're going to move our methyl group, instead of pointing up, it's going to point down. Okay, because now if we take a look at our substituents attached to the 2 carbons in the double bond, what do we get? Attached to carbon 3, we have a carbon. And then, of course, we also have an invisible hydrogen. And then attached to carbon 4, here we have a carbon. And up above, we have an invisible hydrogen. So what do we notice about our 2 carbons, our 2 highest priority groups? Well, now they're on opposite sides of the double bond. So we have an E isomer. So if we were to name this molecule, it would be E3 pentan 2-one. The last thing we need to consider when naming molecules with aldehydes and ketones is the possibility of having R or S isomers. Now, what does that mean? Let's say I have a molecule with a ketone like this. We'll get to how you decide if it's an R or S isomer, but for practice, go ahead and pause the video and name this up to what we've learned so far. So you should have got that this is 3-methyl hexane 2-one. Now the only thing missing is we have to add on in the front of our naming here, whether this is an R or an S configuration. Now, what does that mean? Well, this molecule has what we call a chiral center. And just to review really quick what a chiral center is a carbon that's attached to 4 different substituent groups. So that means, for example, it's a carbon that can't be attached to 2 hydrogens, or a carbon that can't be attached to 2 bromines. Every group it's attached to, remember carbon likes to have 4 bonds, so it's attached to 4 groups, has to be unique. So can you take a look at this molecule, pause the video, and see if you can find the chiral carbon in this molecule? So hopefully you found that the chiral carbon in this molecule is right here, next to our carbonyl carbon. So how did I know this was a chiral center? Well, let's take a look at the substituent groups that are attached to our carbon here. On the left side, we have this hydrocarbon chain. Okay, so that's one group. Then, of course, we have our methyl over here. So that's a completely different, unique group. Then over here, we've got our ketone. So that's a different group. And then finally, not pictured, but we know it's there, we must have a hydrogen because every carbon must be attached to 4 groups. So let's go ahead and draw in that hydrogen as a solid wedge facing towards us here. So as you can see, this carbon has 4 unique groups, so it's a chiral center. So now quick question, could a carbonyl carbon be a chiral center? Like, could this carbonyl carbon be a chiral center? No, a carbonyl carbon can never be a chiral center because it is double bonded to an oxygen, which means that it's like the same thing as if it was single bonded to 2 oxygens separately. So because of that, it's not connected to 4 unique substituent groups. So now how are chiral carbons related to whether we have an R or an S isomer? Well, if a chiral carbon has 4 different groups, those 4 different groups can be arranged in different spatial ways. And we call those different ways that they can be arranged enantiomers. Now, enantiomers are non-superimposable mirror images of one another. So basically we just arrange the groups in different way so that they're mirror images, but you couldn't put them exactly on top of each other. They're not superimposable. And the R or S system is just going to tell us what arrangement we have around our chiral carbon. Whether we have an R arrangement, R stands for rectus, which means right in Latin, so like a right-hand arrangement, or whether we have an S arrangement. S stands for sinister in Latin, which actually means left-hand arrangement. And it's important to know whether we have an R or an S enantiomer because that's going to tell us which way the molecule. Now let's take a look and figure out if this is an R or an S enantiomer. To do that, we're going to number each of our 4 groups by its priority. In deciding priority, we're going to use those same Kahn-Ingold pre-log rules. We're going to take a look at the elements that are directly attached to our chiral carbon and see what their atomic number is, and the elements with the highest atomic number get priority. Now, if we have a tie, for example, over here, we see that the chiral carbon is attached to a carbon here, and a carbon here. So to break that tie of the carbons all having the same atomic number, we're going to look at what those carbons are attached to. So this carbon off of the methyl, we know is attached to 3 hydrogens. So I'm just going to write the hydrogens out here. Hydrogen, hydrogen, hydrogen. This carbon on the hydrocarbon chain in pink, it's attached to another carbon and 2 hydrogens. Lastly, in our ketone, this carbon over here in yellow, this is going to be attached to oxygen twice, right? Because there's a double bond. We count each of the single bond within the double bond as being one element. So this is like this carbon is attached to 2 oxygens and, of course, another carbon. So what's going to be our highest priority substituent of the 4 groups? Well, obviously it's going to be the one with oxygen because oxygen is going to be our highest atomic weight here. So the ketone here is going to be our first priority group. So what's our next priority group after our ketone? Let's take a look at what we have. Well, the green group, we've got 3 hydrogens, and the pink group, we have 2 hydrogens and a carbon. What do you think is going to win in terms of atomic number? Well, carbon has an atomic number of 6 and hydrogen has an atomic number only of 1. So anything with a carbon is going to win over 3 hydrogens. Okay, so our second priority group is going to be this pink hydrocarbon chain here. And then lastly, we're left with our green methyl and our red hydrogen here. Of course, in the methyl, our chiral carbon is directly attached to a carbon versus a hydrogen. So since it's directly attached to a carbon, that carbon again is going to win out over that hydrogen. Now, whenever we have a hydrogen attached to a chiral carbon, we always know it's going to be our 4th priority group. So if you want, instead of finding your highest priority group first and going from there, you could actually start by finding your hydrogen and naming it as your 4th priority group. Okay. So now what we're going to do is we're going to look at which direction these numbers are going in if we go from least to greatest. So here's 1. If we follow that 1 around to 2 and then to 3 and then 4, we're going in that direction. So for figuring out whether this kind of rotation of functional groups mean you have an R or an S enantiomer, there's a little helpful trick you can use. Just go ahead and draw the letter R and the letter S, and then you're going to draw arrows at strategic places in them at the top parts. So in this R, we're going to draw an arrow here. And notice, what would that arrow mean? That's like an arrow going clockwise, right? If we completed the circle there. So our R enantiomers are going to be clockwise. For our S enantiomers, we're going to draw an arrow here. And what would that be if we completed the circle around? Notice that we're going counterclockwise in that case. So our S enantiomers are going to be counterclockwise. So in this direction, notice that we're going counterclockwise, except for one thing. Whenever our hydrogen is facing towards us, as we know it is in this case because it's a solid wedge, we have to reverse the direction. So this would have been the S direction, except because that hydrogen is facing towards us, we're going to say it's the R direction. So this molecule here is going to be R, and usually it's written in parentheses with a dash, so R3-methyl hexane 2-one. Now, what would we have to change in this molecule to change it from being in the R direction to the S direction? Well, how about if instead of the methyl facing away from us, we made the methyl face towards us? Let's take a look at what happens there. So here's this exact same molecule, except now notice that our methyl is a solid wedge, which means it's facing towards us. And we still have our chiral center highlighted in yellow here. Now let's take a look if we number our priority groups that are attached to that chiral carbon. So first we can go ahead and draw in that hydrogen that we know is hiding there. But this time the hydrogen's going to be facing away from us. That means whatever rotation we get, whether it's clockwise or counterclockwise, we're going to stick with that. We're not going to have to switch the direction at the end. Okay, now everything else is going to be the same. This carbon that's attached attached to the oxygen twice is still going to be our number one priority group, followed by this carbon, which is attached to at least one other carbon. And then, of course, we're going to have our methyl. That carbon is only attached to hydrogens. Lastly, we're going to have our hydrogen, which is facing away from us. So if we trace our numbers from least to greatest, we're going to go 1, 2, 3, 4. So this direction is going to be an S. Just like if we continued this top part of the S around here, we'd be going counterclockwise. So in other words, we have S3-methyl hexane 2-one here. Now, if you find it tricky to calculate the priority groups when you're within a larger molecule, you can always take that chiral carbon and redraw it, just what's attached to it separate from that molecule. So let me show you what that would look like. On this first R enantiomer, so here we have our chiral carbon in the middle here. What's it attached to? Well, going this way on the yellow group in our ketone, you've got a carbon. What's that carbon attached to? We said it's attached to 2 oxygens and another carbon. If we take a look at our green methyl group here, facing away from that chiral carbon, what do we have? Well, we've got a carbon and then attached to 3 hydrogens, all right? If we take a look at our pink hydrocarbon chain, here we've got a carbon that's attached to another carbon and also to 2 hydrogens. And then lastly, facing towards us, we have that hydrogen. So if you draw it just as part of the molecule, then it would be easy to see that, of course, our hydrogen is our lowest priority group. Anything with oxygen is going to be the first priority group over our carbons and hydrogens. The thing with the second most carbons is going to be our second priority, and the carbon with all the hydrogens is going to be our third priority group. So then you just trace around your numbers, and of course, you end up with an R enantiomer. So we really covered a lot of ground about how to name aldehydes and ketones today. So first we talked about prefixes and suffixes for ketones and aldehydes. So generally, when you name a molecule, it takes this format. You have your substituent groups, which are all of your functional groups other than your highest priority group, and we name those by the prefixes. And then you have your root, which is your longest continuous carbon chain that contains the carbons in the highest priority group. And then you have your suffix. And we talked about what our prefix and our suffixes are for aldehydes and ketones. So our suffix when we have an aldehyde just on its own is going to be Al. For ketones, it's going to be -one. But then when we have aldehydes or ketones within a larger molecule and they're not the highest priority functional group, for example, in a molecule where there's a carboxylic acid, which is higher priority over aldehydes and ketones, well, then an aldehyde, we know that its prefix is either going to be oxo or formyl. And a ketone, its prefix is going to be either oxo or keto. Then we got into the idea of alkenes. What happens if we have a molecule with an aldehyde or a ketone that has double bonds in it? Well, first thing we're going to do is we're going to change that root from an an for alkane to an en for alkene. So for example, instead of pentan, we might have penten with an en. We also talked about the idea of E and Z isomerism, and that has to do with whether our highest priority functional groups attached to the 2 carbons in our double bond are on the same side of the double bond or on opposite sides of the double bond. If they're on the same side of the double bond, then we have a Z isomer. If they're on opposite sides of the double bond, then we have an E isomer. Finally, we finished off the lesson by talking about what happens when we have molecules with aldehydes or ketones that also have chiral centers somewhere in the molecules. Remember that that carbonyl carbon is never going to be a chiral center itself because it is always double bonded to an oxygen, which means it's not attached to 4 unique groups like a chiral center must be. Here, we said that to figure out whether we have an R or an S isomer in our chiral center, we're going to look at the 4 groups that the chiral carbon is attached to, and we're going to number them in terms of priority, according to atomic number. Just like priority for determining our groups in E and Z isomerism was according to atomic number as well. So after we've numbered those 4 groups, we're going to just draw an arrow of rotation to connecting those groups from least to greatest. And then if it's clockwise, we know that that's going to be an R enantiomer. And if it's counterclockwise, we know it's going to be an S enantiomer. Always remember though, that if there's a hydrogen, that hydrogen has to be facing away from you. If the hydrogen is facing towards you, as exemplified with a solid wedge, whatever direction you got, if, for example, the priority groups showed a counterclockwise direction, you're going to switch it. So then it would be a clockwise direction. So that's everything you need to know about nomenclature of aldehydes and ketones for the MCAT. Next up is physical properties, so check out the next video.